And we keep going with some more muscle topics. In this video, we're going to look at the graded response. How can your muscles lift both light things and heavy things? And the answer may not be quite what you think it is. What is TREPA, and why does it suggest that we should warm up before we exercise? The difference between isotonic and isometric contractions, and some basic healthcare considerations that deal with the muscular system. So, it's a question that maybe you haven't thought about so far in our muscle discussions. How can the muscles adjust and lift something heavy and lift something light? The key term here is graded response, that our muscles have the ability to grade or to adjust their tension or the amount of force they can generate. And as you'll see on the next slide, there's really two mechanisms that are responsible for this. So the first mechanism is to get more muscle fibers involved, and we'll consider that one in more detail in a moment. And the other one I'll just mention is to increase the frequency of the stimulation on the muscle. But let's start with this one, getting more muscle fibers involved by nervous stimulation. To understand this one, you need to understand this key term here, motor unit. A motor unit is going to be a neuron, a nerve cell, and all the muscle fibers it controls. So we have two motor units shown here, and we see the different colors here indicating them. Motor unit 2, the red one here you see, is going to be that neuron controls this one, this muscle fiber, and this muscle fiber. The other motor unit down here, motor unit 1, is actually going to be this one and this one. So notice we have 5 muscle fibers here involved in 2 motor units. Now let's be again clear what a motor unit is. If a neuron fires a signal down its axon, it's going to stimulate the motor fibers or the muscle fibers it controls. So if we wanted to, let's say, have a very light muscle contraction or very small muscle contraction, maybe only motor unit 1 fires, and 2 muscle fibers out of the whole muscle are going to shorten, and we're going to have a very small minor contraction. Maybe we have something heavier and we fire motor unit 2 instead, and therefore we get 3 muscle fibers contracting. Or maybe it's something where we need all 5, and therefore we get motor units 1 and 2 firing. So you see here the strength of the contraction depends at least in part on how many motor units are involved, and we'll explore that more in just a moment. But I want to mention one more thing about motor units, this idea of giving fine motor control. A motor unit, again, is a neuron, all the muscle fibers it controls. Think about what the relationship would be between fine and very coarse movement of muscle. In other words, we'll give you an example. The motor units of the eye. You have some very delicate, very precise movements of the eye. Do you think you're going to have a neuron controlling just a few muscle fibers or a lot of muscle fibers? And it's a little bit paradoxical, but a fewer number of muscle fibers. That is, you have much more delicate control if a neuron affects 2 or 3 muscle fibers and has a very delicate contraction versus if it were to affect 100 or maybe several hundred. An example, your gastrocnemius, your calf muscle, one neuron may affect 2,000 different muscle fibers, but you don't need a lot of very delicate movement of your gastrocnemius. You need a contraction or not. You don't need the delicate movement you expect with the eye, the very delicate back and forth or up and down that we see with the muscles of the eye. So that's a key point. Motor units, again, a neuron, all the motor fibers it controls, muscle fibers it controls. The fewer the muscle fibers in a motor unit, the more delicate and the more fine control that motor unit is going to have. But let's move on again to this same idea with an idea called recruitment. Let's say, again, you want to lift an object and you reach down and you begin to pick it up, and it actually is heavier than it looks. What you may see is a process called recruitment. Initially, motor unit 1 in whatever muscle we're talking about is going to be activated first, and some of the smaller fibers, some of the smaller motor units may be activated first. Then you may actually activate motor unit 2, which is going to be composed of some larger muscle fibers or more muscle fibers versus motor unit 3. In other words, this idea of tension, of muscle strength, is going to be a sort of a series of increasing the number of muscle fibers involved, which will give you an increased tension. So this is what recruitment is. It's that smooth, gradual, you're lifting gradually, the smooth, gradual recruitment. You're bringing more muscle fibers into the contraction so that you get a stronger contraction. So that's one way that we can give a graded contraction, is that we can have recruitment. That is, we can increase the number of muscle fibers involved in the contraction. The other way deals with the frequency at which muscle fibers are stimulated. So let's look at this graph here. This will look a little familiar to you because we considered before the idea of a twitch, that there's going to be a stimulation and there's going to be a latent period, then there's going to be a period of contraction and a period of relaxation. So we saw that before. And so whenever you see S down here, that's the stimulation. So we've seen this. You stimulate, there's contraction, relaxation. Okay, what if you stimulate it, and as it's beginning to relax, you stimulate it again? Well, notice what you see now is a slightly higher tension. You see it's higher here than it was there. Why is it higher? Why do you think it would kind of piggyback on the first one? What is going on during this part of the cycle? Relaxation of muscle fibers. What is occurring during relaxation? What is being moved from one place to another? Hopefully you might remember that we are moving a particular ion, calcium, back where? Back into the sarcoplasmic reticulum. We're actively transporting, we're pumping it back in. If there's no more stimulation, it's all going back into the sarcoplasmic reticulum, and when calcium is removed away from the troponin, it peels off the troponin. The tropomyosin is rolled back into position. It blocks the binding sites. Myosin can't bind actin, and the contraction ends. So if we were to stimulate the muscle here, that is, before it is fully relaxed, there's probably going to be lingering calcium still available. So if we hit it again with another impulse saying release more calcium, that calcium is going to piggyback on the calcium that's already there, and therefore we can have potentially more troponins bound by calcium and more tropomyosin moved out of the way, and therefore more myosin binding actin, and therefore a strengthened contraction. So that's why we see the piggyback effect. What if we get really cruel and we stimulate it and stimulate and stimulate and stimulate and stimulate and never give the muscle a chance to relax? You see this again, this ramping up, if you will, of increasing contractions all the way up to a certain point. So subsequent stimulations with only partial relaxation. What if we really go for it and we stimulate, 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 stimulate all the way through and never give the muscle a chance to relax? Why does it not keep going all the way up still? Once you've maxed out and you have essentially every myosin binding, every actin, and everything is, there really isn't any way of increasing the tension beyond the max, you're not going to get a increased contraction beyond a certain point. We call this fused tetanus. This is not tetanus like the disease tetanus. Tetanus here just means complete contraction. And eventually, though, even though we're stimulating it, this happens. Why? The muscle is fatigued. The muscle can't physiologically respond again anymore to any more stimulation, so the muscle fails, okay, until it's able to reset itself. So again, to review, you can increase a muscle contraction strength by getting more muscle fibers involved, or by increasing the frequency at which you stimulate them up to a point of maximum contraction. Okay. Here we go. Moving on. Let me show you this about Trepa. And Trepa actually refers to what's called a stair step. I think it's a German term. What you see here is a little bit of that stair step. You see a stimulation, a stimulation, a stimulation, a stimulation, and we see the twitch cycle of contraction, relaxation, contraction, relaxation, contraction, relaxation. Notice initially the first contractions are kind of wimpy. We don't get a lot of tension on those, and then eventually the contractions here are nice and clean and tall, and we see the same thing down here too. Why are the initial contractions not as powerful? Said differently, when you first start contracting a muscle, maybe you're about to do some running, and you're doing your first running, your first steps, or it's first thing in the morning, your muscles really are not warmed up yet. How come those first contractions aren't good? What really isn't fully present? Calcium. So if you had some contraction and relaxation of your muscles, and you did have calcium more available to your muscles, you were increasing blood flow because you've increased some activity in the muscles, you've increased the oxygen levels, you've increased the efficiency at which muscles can work. So this suggests, in part, reasons it's good to have some warm-up activities to get your muscles going. You don't see professional athletes just run out of the locker room and then just go immediately do stuff. There's always a stretching cycle and a warm-up cycle and a getting ready to go cycle. That's in part to make muscles more efficient. It's also helpful to prevent injury. A couple of things to end on here. I don't want to spend a lot of time on isotonic and isometric contractions. You will hear these terms in certain applications, so I do want to mention them, but don't stress here. Here's what I want you to focus on. There can be a contraction of a muscle, and it can shorten, like you see here. This is going to be an isotonic contraction. That is, we have a 3 kilogram weight on here. Okay, the muscle can develop enough tension to overcome that, and so it's going to shorten. It's going to get smaller. So here's the stimulation. Here's the stimulation. We develop our peak tension, and notice this is the contraction of the muscle. This is getting shorter over time. It can get shorter because the muscle can actually overcome that load and can get smaller. It is possible, though, that you can have a contraction of a muscle and it not move the load, as you see in an isometric contraction. Here's a 6 kilogram weight, and this muscle just can't shorten enough to move that. It just physically can't move it. There's going to be a contraction. There's going to be, that is, the starting of the tension, but imagine myosin grabs actin, and that's all it can do. It really can't pull it. The force is too heavy on that for it to pull, and therefore the resting length of that muscle, come back, cursor, the resting length of that muscle doesn't change. So do we ever see isometric contractions? Sure. Let's say that you're carrying in a bag of groceries from the grocery store, and you've got your groceries there, and basically your muscle is not overcoming that load. It's kind of under some tension, but it's not really, not lifting the groceries like this. You're kind of holding them there. That'd be isometric. Back in the 70s, that was sort of the exercise trend, isometric exercises. You'd do a lot of things like this. You'd push against your own muscles. And by doing this, your muscles are not really getting shorter, but they are developing some tension. And that is supposed to obviously increase their physiology, make them a little more efficient too. So isotonic is when a muscle develops tension and shortens. Isometric is when it develops tension but can't shorten because the load's too much. Okay. Finally, some healthcare considerations and what happens when we age with muscles. If you look back on your skeletal system healthcare considerations, most of these are going to be the same. That is, you're looking for things like people complaining about pain or complaining about soreness in any part of their body following activity or even in the morning. But additionally, specific to muscles, you need to be aware in having conversations with patients or parents about developmental issues. For example, a child who is delayed, a child who isn't crawling after age 1, or who's not walking after a certain point. It could be the child is just stubborn, or it could be the child actually has a muscle issue where it's not developing the musculature or the muscle control, and that could be an indication of a serious disease. People have ongoing pain or cramping or weakness of muscles. It could suggest metabolic issues, disease issues, dietary issues. So again, if they mention that, it's something to be aware of. A functional assessment. Can they do activities that require ROM, range of motion? Can they put their dishes up in a cabinet? Can they lift their shoes off the floor? Can they take their clothes on and off? If they say, well, I can't get my hands over my head, then those are again concerns where you'd want to follow up with a doctor and make sure you mention that they have limited range of motion, and that could suggest some concerns. And again, things like inspection, palpation, range of motion testing, muscle strength testing are all things that are routine to evaluate this system. Finally, what happens as we age? There'll be no surprises here. We have a progressive loss of muscle strength and of muscle mass as we age. Just like most tissues, as we age, they slow down, they repair themselves less efficiently. We do see a decrease in maximal strength, slowing of reflexes, and loss of flexibility. Now, before you start going for a rocking chair and giving up on life, these can be reversed to some degree within physiological limits. When I go to the YMCA to work out, I see some guys much older than me lifting some pretty heavy weights. I see people older than me who are doing quite a few activities in aerobics, and they're very active. I also see people younger than me who have noticeably some deficits, who have loss of flexibility, or they have loss of muscle mass, because like any tissue, muscle responds to our activity level. So that's why they found that even doing aerobics in nursing homes is not like aerobics at the Y, but even doing some walking activity, as we mentioned before, the skeletal system, any activity stimulates osteoblast. It stimulates muscle tissue. It stimulates blood flow, which keeps the tissue more vibrant and healthy for a longer period of time. You might get to the point where you have to buy a floral bathing suit and you're in the water doing this. That's fine. But we know that activity can slow down or even reverse some effects. And that's why do not dismiss the idea of staying active and keeping your patients active as long as you can. That will do it for this video. We've got one more to go. Thanks.